Yesterday I had to stop for the day really early. At first, I wanted to think about how we could get the correct reward into the row-gather map reduce kernel. I thought about that for like an hour, and then some really bad weather rolled in, and I had to stay away in order to protect my electronics. Even though I have a UPS, it won't protect me from a direct lightning strike. And even though I have a warranty, that still means there's still a question of whether the company will honor it. And then I'd have to wait for like weeks to get a new computer. So it's better for me to just stay away for a few hours while the storm passes. And I did figure out how to do this. So we're going to have to do it as a part of a separate video rather than the CFR one, because it's going to involve some language hacking, and the solution that I've come to is pretty interesting, to say the least. What we're going to do is, instead of having to share this reward variable in memory in order to distribute it to the threads that need it, we're going to automate that. If you look at the row gather kernel, you'll see that we have these shared tensors. Share from, share to map, share to reduce. And instead of doing it like this, we should in fact be doing it... I mean, you can see what we are doing here. We're creating this tensor CUDA, we're creating this shared tensor block, then we're assigning the values to it. And then... wait, share to reduce... yeah, we're just... we're not assigning anything to this one. This one just simply... Okay, so sorry for getting distracted. But anyway, what I wanted to say is that it's actually possible to do this part automatically. So that whenever you pass a function into a loop, it just gets all the free variables from the function and then substitutes them. And then we won't have to make the same mistake that I've been making previously. Like here I forget to pass the reward, and here I'm passing in the wrong policy update. Or rather, this policy update is from the wrong thread. And I might have other errors of that sort that I missed. I have at least 2 errors here, and yeah, this is pretty bad, and the cost to fix it is pretty severe. I don't want to have to think about shared memory right here. Like, I don't want to create a shared tensor, then you have to exchange the variables manually, and they have to put in barriers. That will really make this significantly harder. Well, let's resume. I just got to go to the bathroom for a bit. We also need the hash set. Damn, this... okay, what do we want to do with this? I'm kind of confused. Okay, so this is an order dictionary. I mean, because it's ordered, we can actually replace the stuff in it. Like, yeah, I mean, we could just create something like a hash set, then iterate over it, and then add the keys as they come, but I'm not sure whether that would preserve the ordering. I mean, I guess what really matters is whether one hash set is equal to another. Let me just think about the hash map a little bit more. The hash map, like in join points, like we should have something like RE hash map. Const node, our data. Yeah, we're converting it to an array like this, and we are doing that so we can actually compare the arrays for equality. We could compare ordered dictionary for equality. At least I think they don't have a built-in equality operator, but these two, the arrays, we can do that easily. Like, I mean, let me demonstrate, whatever. Let A equals 1, 2, 3. And then we can just do A equals B, and it will actually compare it structurally. And it's kind of annoying how it doesn't pin it automatically, instead it just closes it. So, okay, yeah, you can see what happens when I pressed Alt-Enter to send it to the F# interactive. If we make one of the elements like different, then the arrays are wrong. And we need the equality comparisons. And we cannot convert a hash set to an array because it's not ordered. If we converted it a hash set to an array, it might be arbitrarily different between compilation runs. So it's not good. I guess we'll just raise an error here. It seems like hash sets are a black sheep. Whatever. Let's also pass in the language environment. Raise type error. Mutable compile time. Hash sets cannot have their And at a certain point you have to even wonder why these hash sets exist, because we can get pretty much all of their functionality using hash maps. Who knows, maybe in some future version of the language we'll remove them. It doesn't really matter. Oh yeah, this is a reference. Oh crap. Ref. It's also possible to just use a prefix operator like this. Yeah, not bad. We want to copy this rather than passing the same reference. Yeah, I like this. This should be good enough to replace the free variables in an expression. So let's make use of it. We're going to use the bookmark to get to the other place. And we're going to do data free vars replace, and then s. We're going to pass in this dictionary, and we're going to pass a. One good thing that Visual Studio does have is the shortcut to save all files, Ctrl-Shift-S. I frequently use that. And I actually had to assign a shortcut for that in Visual Studio Code manually, because it doesn't have it. Oh yeah, this is basically how you extend the partial evaluator in Spiral. You can do some pretty neat metaprogramming in it. And imagine how long this would take to land in something like C++. It will basically never get there. And since I have my own language, I can put it in 5 minutes. For anybody watching this, if you can ask me, if you're using Spiral, you can ask me for features, especially if it's something like that can be easily added in the partial evaluator, like this. It's no big deal. I mean, something that would change the language at its core. I mean, I probably refuse that unless you paid me to do it, but something like this, and if it's not too hard to add, and if it's useful, then we might add it. There's a good chance that would happen. Okay, let's VS Code plugin, and I have to wait for it to finish building. More than a few times I've run the plugin too early. I mean, okay, it finally compiled, and it took 26 seconds. It just keeps going up and up, the compilation times. Okay, so let's close this terminal. And if we build a file, yeah, now we have this. So we could replace the free variables. Okay. Wait, do we have to replace one free variable with another? I mean, hold on. I mean, we could just replace a free variable with a data, with an arbitrary data term. Yeah, but before we commit to a particular direction. We should think about this for a bit. Like, I just got the free vars from here because it was the easiest. But that does limit what we can do. Maybe we could replace the free variable with a tuple or of something. It's kind of risky to do this. For example, it might if you have something like a nominal, it might end up constructing them incorrectly. Okay, this is one way. I mean, this is a way of doing it, but yeah, it has its own kind of worms. It's one thing to replace a slot. A slot is a different thing than replacing a free variable outright. Replacing a free variable outright, with this feature, you could get around the type checking in union types and nominals. Okay, I just did it without. I should have thought about this a bit more. But I guess I'm not really that good at thinking away from the keyboard. I did obsess about this a lot, which built the motivation to actually do it, but... okay, where the hell is the nominal? Nominal... Yeah, we only do the type checking during construction, and it was simply never expected that we'd be able to swap a free variable arbitrarily. So what do? Do we just maybe instead of doing this, do we then take the slots of a function and replace that one instead? Okay, how about this? We can only replace a free variable with another free variable of the same type. Yeah, I mean, that's what we want to do anyway. We don't have to replace a free variable with an arbitrary data type or an arbitrary runtime variable. I do want to make the features as safe as possible, even though I cannot always do that. The only place where the partially evaluator is really unsafe is that it treats the types of for alls and existentials as any. It's similar to how the any type works in TypeScript. If L, okay, as A is going to be TA L TB as B. If TA equals TB, then the free variable. Got show type ta expected show type tv, and whenever I write got and expected, it's absolutely never. I never have a good idea which one should be like got and which one should be expected. Maybe whether this one should be TB and this one TA. It's pretty much always wrong, as far as I'm concerned. Yeah, now this free vars place that does make sense. We can just replace the free variables like this. And we're going to use that in order to implement the, I don't know, the distributing loop. Let's call it like that. Maybe I thought of names like sharing loop or transposing loop, but transposing is not the kind of thing we have to. I mean, a transpose is a specific matrix operation. It's not something with. I mean, we are doing that here, but yeah, maybe we could call it the transposing loop. Yeah, we'll call it the transposing loop. Okay, so I'm going to. Okay, let's publish it again. Let's run this. Let's test this. We're going to make this. We're going to simplify this a bit. 1 I32, 2 I32, and this is just test. And okay, we have the free variables, and we're going to do something like struct map plus 2 free vars, and we're going to free vars replace, and the first one is going to be f. And the second one is going to be free vars quote. Now, if we build this, let's see what comes out. The main function should have for all. Oh, let's see what happens here. Oh yeah. I'm trying to. In addition to just returning the free vars, it does that annoying. It returns that annoying unit type at the end. Match x with, let's see, x I32 x plus 2 I32, and otherwise x and just return the x. I guess this should work. We can make this function. Okay, so the two expressions need to have the same number of type. What? Wait. Free variables. That's what I meant to say. Yeah, now we're saying the two expressions needs to have the same number of free variables. But shouldn't they be the same? What the hell is going on? Okay, let's do print static. Print static. Free vars. And if you look at the terminal, I32. Wait, did we maybe simply get the conditional wrong? The other way around, I mean. Oh yeah, like this. Wait, what the hell is going on here? Why is there a closure? Oh yeah, we're returning the closure for this from this. I mean, so we should yeah, let's apply this. The return type is basically wrong. Now let's see whether the replacement worked. And I mean, I can already see that it did. Yeah, it's returning 3 and 4, and initially we were passing 1 and 2. So the free vars replace works, and what we want to do is use that to... We'll get the free variables, store them into shared memory, and then we are going to shuffle them from shared memory and replace them in the relevant function. So it's going to work. I'm going to make a new module in Corcuda. I guess we'll name it T-loop. The transposing module. I guess let's have a core base. And we're going to okay, how we do it? How we do this? Okay, let's just name it iter for now. We're probably going to make it a for loop later. But for now, let's just do this. It takes in f. Okay, let's make this b, and you know, a equals thread threads per block. So that could be like 512. We have to assert that b is less than threads per block. Okay, assert. I mean, less than or equal of threads per block. The inner dimension must be mini block. Okay, thread. Oh, transfer mini block, transfer block. Okay. And in fact, no. The inner dimension, the number of threads per block must be divisible by the number of by the inner dimension. Okay, let me just do a little check. A few videos ago I sent an email to Moergo and they told me that Moergo, that they're going to get the whole tap variants. No wait, where's this guide? Let me take a look at my layouts. And clone to edit, I guess. I guess it's using Git under the hood to save the layouts. So what I want to do is edit this from being the mod tab to I guess they still haven't added the hold tab. They said it would be very soon, but keep as behavior. Tab. Okay, never mind. I guess I'll have to. I just have to bear with it for longer. I mean, what happens when I press something like Shift? I get an underscore, but if I press Shift and press another key too early, then I get like you know, capitalize the letter, and I kind of want this to be a bit faster, so I can type normally instead of having to delay my keystrokes purposely. It's actually going to make my typing slower if I acquire this as a habit. It's very annoying. Okay, we don't need the transfer block. The transfer block equals 0. Yeah, this is the most important assert that we need. Okay, now I really wish that the free wars. The free wars wasn't returning that fucking unit type at the end. If it wasn't, we could just put everything in the tensor. Free. I mean, pretty much nobody will be using the Upman backend at this point. And we are only using the free wars, I think, in the Upman backend, maybe. I mean, we can check. Spiral compilation tests. Free wars. Oh crap, so we have this turned down. Aha, we do have it in real core. It seems like I forgot. I mean, we have it in a bunch of free wars. Aha, we are using that in loop. Wait, is this really right? I think this version of should be wrong. Yeah, this is the correct version. Yeah, I mean, I guess we do need Yeah, we have to change a bunch of things. If you change the how free vars works. The main problem is that we cannot just get the free vars and then take the type of data and put it in the tensor, because the tensor, I don't think it cannot have arrays of unit types. It cannot have any field that's a unit type. It's that very small thing that is annoying me. I mean, we could do something like an alternative free vars. But this is such a natural way of doing it. I mean, yeah, it kind of seems like a quibble, but it's really not. Being able to simply just take the type, put it in a shared tensor, and then read from it will make what we want to do a lot simpler. And we're getting blocked because of this. Okay, data free vars. Yeah, that's not actually something that's putting the problem at the end. Okay, let's just try going. Let's just try going with this, and we'll see how it feels. Do we really want like two versions of this, or? Block parsing, free vars. I mean, the way that we were using free vars in other places doesn't make sense. I can't really say that what we'll do here will be better. It's simply more useful depending on the context. So we have the array fallback, and if x length greater than 0, then array map it's gonna complicate things when what should we return if the free vars are essentially not there? Before we do this case, let's think about that. Yeah, it would help a lot if the tensor allowed the unit types. Okay, let me pause here. I might as well have breakfast here, so I can think about this issue and decide what I really want to do. We'll resume shortly. Let's resume. So we're going to let's do a test so we can take care of the void arrays. First, let me show you what the problem is. Let's make a test. Let's raise the table. in open base. New main. Let's do a run. And this is just running an empty kernel. Let me just take a look at the sidebar. Yeah, this just runs on. There's so much fucking. I hate all this library code. It makes it so hard to read. Okay, basically we have an empty entry function. And suppose we create an array, something like, you know, create one. Okay, let's create like 16, and this is going to be array I32 build. Yeah, now it creates this array. Suppose we create something like a unit array. Expected it gets something like a compilation error instead of this. Like, why is it even printing this type here? Okay, if we tried running this, it will definitely get an error, because we cannot have void arrays, of course. Array of void is not allowed. Suppose we try the setting and indexing into it. Index 0, index A 0. Okay, let's see what happens here. Void array index set A 0. Just to drive the point home. Here's what happens if we do multiple statements. And this indexing and the setting is fine. Let's take a look at the CUDA code generator. Array index. Oh yeah, so it's like this. What about array create? Void raise conjugate error. I mean, no, we won't raise an error. We'll do line S. Void array create. This was the behavior back in 2018 in Spiral, so I kind of didn't care about void arrays since then, but we'll just bring back that kind of behavior from back then. Oh fuck. Okay, let's get rid of this. We don't need a version that doesn't have an unit type. Now let's publish this again. We also have to... oh, it's already closed. void array create, void array index, void array set. Yeah, perfect. Now we can have void arrays, but this isn't the end of it. The problem is that if you use something like tensor create shared, tensor create shared, open tensor CUDA 16. Okay. This is going to go. For fuck's sake. Open tensor M. Of course, if we try running this now, it should work. But if we if we build this, as you can see, now we still have the same problem from before. We aren't using the inbuilt array create, but instead we're using whatever is in the tensor CUDA module, which is a macro, and that one is still printing out void. So let's see. Tensor create. And yeah, this is a problem. At the very least, we'll just do a type case of t. This is not the way that the regular arrays will be testing for whether the void type is. I mean, they're testing whether the type is a void in a much more general fashion, but here we'll just do a special case for the unit type. Take st with this, then array. I mean, why aren't we getting an error that... oh, this is in top-down. I see. The macro needs an annotation. Aha, so this is a macro, and this is a fucking string. The macros need the $sign. It's not a top-down function. Oh, wait, oh yeah, it's because it's in here's the real keyword. Okay, so that takes care of that. I mean, I don't think this really needed a real keyword before, but now it does. So, I mean, a bunch of types could be void. One void type is this unit. Another void type are, I mean, the other void types would be symbols, and there could also be empty records. And those are basically the void types, and we're only testing for one kind of them. Oh, well, whatever. I I mean, if it's an empty record, it won't create any arrays at all. You can just map over the record, see that there aren't any types, that there aren't any elements inside the record, and leave it empty. And that's easy enough. As for the symbols, yeah, that's a bit more complicated. But we won't be putting symbols into arrays anyway. The main problem is this unit type, and that's and we're taking care of that here. So, and when we are indexing into an array, we are already thinking about the void case, so it's no problem. Let's test this out. B fuck. Okay, this wasn't good enough. Let's do it like this. Yeah, okay, great. Void shared array create b0. Because we put this variable inside the macro, it won't print it out as a void pointer. Okay, great. It might try indexing, you know, if we try returning this void array from somewhere, we'll run into trouble. It will try taking v0 and maybe returning it from a join point, and that will lead to a compilation error. So we have to be careful, but we will be careful. I mean, it's impossible to really get a serious error with this. At most, we get an error that it cannot really fetch this variable from anywhere when compiling a CUDA program, but otherwise it will be fine. Well, let's resume. Now we've dealt with void arrays and void shared arrays. What we have to do next is actually get back to working on this loop. So, okay, we're going to let's make it real. Open real core. You know, free vars of f. Now we have the free variables here. And if we wanted to create a shared tensor, we can just do open core CUDA, open open what? Open tensor CUDA. Oh yeah, we are in core CUDA. Okay, never mind. So we don't need to open it. What I'll do is now create a shared tensor. You know, shared. Let's see. Tensor create shared. But for this, I think we're going to have to pass in the types. So let's see. DL, okay. The dimension, the type of the dimension, and the type of the element. So this is just int, and this is the type of the FV array. I mean, of the FV variable, which is some kind of a tuple. And now what we will do is, yeah, but let's pass in the threads per block. And yeah, this is basically it. Now, now let's see. We have to set this. You know, this is yeah, this is kind of, yeah, it's kind of complicated to have to apply the type variables by hand every time. I guess we'll have to do it. There's no way around it. I mean, bottom-up programming is simply tedious. Like, there's no helping it. Okay, so where is it? Tensor index, tensor set, dim L. Okay. Oh, type case. Dim. We're just going to bind these variables. We're just going to bind these types to new variables. Oh, not bad. Okay, we have the shared. Now we'll set you know, maybe it would be better to just do this in. Okay, let's make it inner body for all dim L. And what I'm going to do is put the shared thing here. The free variables will be of type L. And now we can do tensor set thread index F3 and what? Oh yeah, the shared tensor. The variable dim is unused in the type signature. Okay, let's do tensor dim shared, but you know, this is just going to be like int, so we don't need the dim. Oh yeah, tensor dim L. I mean tensor int L. Open tensor M. Yeah, but we won't be creating it here. Yeah, we don't even need to pass it in. Tensor int L. We're just going to call the body here. So body, and this is going to be FV, and then FV. Yeah, great, problem solved. Now we set the set this to the thread index. We set the free variables into the shared tensor, and now if we wanted to, we could shuffle into it, like we could index into it. So for example, we could do like tensor, actually let's do x equals tensor index 0 shared. And now what we'll do is let's set the free vars to f. We're going to also go into the, let's say, real core free vars. Given a tuple. Put a number. I don't think that many people will be using this, but it serves as a form of documentation to have this function be here. Now we'll try replacing the free variables. So you know, and free vars replace f. We can just index into this tensor. Oh yeah. Let's also put it into core. Free vars. We don't have even the free vars in the regular thing. I mean, this is such a bottom-up function, so I cannot really blame it. Okay, but I do want to put it in the core. Okay, well, let's. This is single. The real core has a bunch of stuff that the regular one doesn't. Okay, never mind putting it in core. It's good enough that it's in real core, and we're going to free vars replace for all t. Actually, for all a, b, a, b returns a. And that's free vars replace ab. So yeah, that's why I wanted it like this. What do you mean he's trying to unify it without something outside its scope? I mean, tensor index, I mean, doesn't it know that this is an int? Why is it messing around? X equals Yes, this is an element. It doesn't know the type of f. Okay, so this would be unit to unit. Oh wait, what the fuck did I do? This should have been a, and it's expecting unit. So let's apply it here. We're going to apply that function here. And we don't need the x anymore. Okay, and we can start testing this out now. So let's see. Let's do an inline main. We're going to do an iter here, and there's going to be some fun function like this. And what we're going to do is have something like reward equals, let's say, -13, like in that other example. But we're also, let's see, I guess we'll multiply it by the thread index. And this is going to be a runtime variable. So suppose we do this and then do a console. Oh wait, we cannot do a console. For fuck's sake. You know what? Let's do the test. Let's do the entire thing in. Test 12. Let's open Corcuda. Yeah, we need to open console extended. Open, core ext. Now we can use console. And then we do write ln reward tid equals thread index. Now let's print this out. We'll get back to this module later. And now I just want something to be in. And right now I just want it all to be in the same file and to have access into the console. Okay, let me take a seat. I had enough of standing. Oh wait, did I accidentally write ln instead of? Did I use the regular write instead of write ln? Yes. But basically, you can imagine what the outputs are. Yeah, it's just reward multiplied by the thread index. And now let's try putting that into iter. This is iter. We also need the threads per mini block. Whatever. I suppose we can just put that as the first argument. And right now this doesn't do anything, so it doesn't matter. Like, let's make it 32. And now this console bright line is in ether. We're running this, and the reward in every thread is 0. If you look at what this is actually doing, it's creating this integer array for the rewards. It's creating this, you know, it's not really creating, but it's kind of simulating the creation of a void array for that unit type. It sets the reward and the unit type into the tensor, then it indexes into the first tensor, and then prints out all of them. So this is very cool in my opinion, because it allows us to swap the variables between threads in an automatic fashion. In the tabular CFR algorithm that we are implementing, we'll be able to use something like this. We're probably going to replace the loop in the gather template, in the row gather template with this once it's done. So okay, I want this to distribute the computations across the threads. So okay, we have the shared thing. Now we have to think. We have the number of threads per block. We have the number of threads per mini block. Okay, let's think about that. I guess we need a projective loop. So it can also be a linear loop. I mean, previously we were kind of, yeah, we tend to use linear loops. Okay, so let's do this here with a projective loop. I don't want to complicate this too much at this juncture. So loop projective. Threads per block, threads per mini block, okay, let's see. Okay, so it needs to be like threads in block. Yeah, threads in block, right. Let's open range_m. Open range_m. Threads in block. This is just a value. Okay, now it will distribute the computation. So this first variable is the outer, and this one is the inner. So we could kind of consider this as in terms of tabular CFR to be the thread ID, and this one is what, something like, let's call it maybe action ID. And we can execute the body of this function here. We'll be using the thread ID to index into it. In fact, we can kind of make a Okay, let's make the threads per minute block something like 4 in the test. Right now we only have 32 threads per block, so it might end up being 20 inputs. Let's make a smaller number of inputs. So we're going to see what we get, and instead of just leaving this as a unit type, let's also pass the two IDs, like the thread ID and the action ID. Let's make this like something like int. Wait, where is the thing? Here it is. Int. And we can actually make this, yeah, let's make this a dim. So for all dim, I dim okay, and this, let's make it, I mean, do we need this assertion right now? I mean, we are using a projective loop, so we don't. So, I mean, I guess we can just do it all like this then. But we were kind of careful to only use linear loops in the past. So who knows? I mean, okay, we're just experimenting right now. We don't need to think too so hard about this. Let's do this. Let's make this dim. So this is the outer dimension, which is the thread ID, and this is the dim. Thread ID, like, let's make this I. Oh yeah. Let's make this 4. I32. Okay, so let's test this out. Let's see whether the indices are working correctly. Let's see what we'll get. And yeah, this is why we call this the transposing loop. As you can see, in the inner dimension, the reward is all completely the same, and the actual thread ID, is this TID here, like TID. But the simulated thread ID is completely different. This is what it's indexing. This is the thread it's getting the runtime variables from, this thread ID quote, and this is the thread whose lexical scope it sees. Yeah, pretty interesting, right? Okay, so I think I'm just going to make this like T loop and projective. And in fact, we can just Yeah, this actually wouldn't be a bad idea of designing these projective loops. Like, I can't really thought about how I wanted to do them at the start, but we could make them an offshoot of range M. I mean, an offshoot of the regular loop module. We could do it like that. Let's take a look at the projective loop in the regular loop module. I forgot what the signature was. I mean, it's probably some kind of range M. I just want to see how it looks like directly. Here's the projective. Is this range dim? Okay, I see. And the body is dim. Oh yeah, okay, not bad. This is acceptable. We're going to make this range M. We're going to make this range dim because we have the range M open. And what's the problem here? Where is this range coming from? I mean, shouldn't it be coming from? Oh, it's coming from here. Wait, but what about the range M then? Where is the range M? It's in CUDA. It's getting the range from the loop. Okay, I see. Okay, so in that case, let's make this loop range. And this loop range is what? It takes in a dim and then returns this thing. And we can extract the from and the by and extend the... Okay, so let's do it like this. Dim width near 2, and it's going to be threads per block and X, or rather it's going to be threads per block. Let's do it like this. Oh yeah, this isn't bad. We'll be able to use this to iterate over blocks or warps or pretty much anything now, because we're passing in this range. The only thing that's going to... Oh yeah, oh fuck. So... Okay, how about we, in that case, make it like... A, B, A, B. Let's do this. Then this is going to be A, this is going to be B. Oh yeah, but we have a shared tensor, and we're kind of assuming this is intended for blocks. So why the hell did I start doing all this? I started getting too fancy. Yeah, I mean, unless we are going to be passing the tensor that's going to be put in directly, then we also cannot. Here we are using the block thread set. What the hell? So, sorry about this. Let's just revert. I mean it. Yeah, let's do it like this. It's fine. But now, what exactly is the problem? It's called projective instead of... right. Projective. Let's try building it. Oh yeah, this is very great, and we can pass in arbitrary inner dimensions into this. Of course, I think what we need is, in fact, something like a linear loop. This is the one. That is the one that we are, in fact, using in row gather. We have a linear loop there, and we just load everything into. If it's greater than, for example, if we cannot be distributed completely, we just load everything into local variables first. Okay, so how will we do this? Oh yeah, we're also missing something huge. We are missing CTA, I mean barrier CTA synchronize 0. Yeah, we need a barrier here. Oh wait, what's even the type of the return type of this? It should be unit, and it cannot see it because of that real segment thing. I mean, maybe it would be better to just, for safety, to do it like this. Then we'll get an error if it's not unit. Okay, so yeah, I think this is good, but for something like row gather, we need a linear loop, and in that linear loop we just load everything into like local variables. But really, that's not actually the job of. That shouldn't be the job. We can just, yeah, we can just do a loop not over the inner dimension but over the outer one. So okay, let's try doing it. We'll try doing a linear version of this. We're going to be using that distribution function like in row gather. Let's open the primitives. And let me just add this video to the timeline. Okay, let's do a linear loop. This is the image, the inner dimension, and so now what we have to do is essentially split this. Okay, let's take a look at the primitives, and we'll take a look at the row gather. ML primitives row gather. And essentially we factorize the inner dimension first for the input tensor. Then we do this loop region split transfer block, and we take the shared dimension, I mean share from dim, that's just transfer block, and the inner dimension. That doesn't include the factorization. And then we get these. And then we yeah, then we do then we project into the shared okay, I understand. Let's put this here. Okay, let's do it like this. Share dim. Dim inner. That's okay. That's just dim. But let's make a dim inner. So now we have the dim block. I think we should Okay, we'll first set it. Yeah, we also need the barrier city, I think, over here, so it doesn't so the other threads don't read from it before it has finished setting. Actually forgot about that. And this is why it's good to have these combinator functions to abstract very important functionality. It's much easier to work on a higher level of abstraction than having to constantly re-implement the features necessary for them. That's why we want to abstract away things like loops and so on. We can do, the reason for that is the reason why we factor out share functionality is both to do less work and to make things easier to think about. So in the future, when I use a projective or a linear loop from this module, I'll know that it just shares the variables across all the threads in the block, and I won't have to think about the barriers or the specifics or how to split the dimensions apart. None of that nonsense. Okay, so what we have to do is now, I think, reshape the shared thing. Okay, where is it do reshaping it? Reshaped const dim block, and then we apply the index block. And this reshaped const dim block, we pass in the shared. Then we apply the first dimension, and the second one will be used for the linear loop. Yeah, now we have a linear loop, dim block, and we can in fact index into the shared tensor. Okay, let's see. Tensor index. Yeah, but we don't really have the thread ID. We have this index inner, and that's really the first part. Okay, what about the second part? I guess we have to reassemble the indices. Calculate the block index. We're just going to get that from here. Thread ID. Actually, no, this is the block ID. or rather, no, yeah, it's actually is thread ID just for the inner dimension. And we also need to calculate the inner dimension, and that's being done like yeah, that's being passed in as a tensor. Okay, this part is correct, but I'm kind of not really sure what I should be doing about this part. It's kind of, yeah, with the projective loop it was very, it was pretty isolated, so it was easy for me to understand what I should be doing. But the raw gather is just so different, it has many things bound within it, so what exactly should I be doing here? It's a good question. Like, okay, let's forget about this for a bit and ask ourselves, how could we maybe change the raw gather instead? Like, we could use a projective loop. We won't have to split this dim block. We could just iterate over the dim inner. Okay, look up like that. I mean, do you want to try redoing this completely? Do you want to try doing this here? Let me pause so I can think about it. I was unsure what I exactly wanted in this function, but I think I have an idea. We're going to assume that this dim inner is 1. And then I guess the purpose of this would start to make sense. Assert dim inner the rather the inner dimension, the threads per block need to be divisible by the inner dimension. I mean, it's the same thing. So we can assume that this is 1. As I was thinking about this, I realized that this is wrong. We're actually applying the wrong strides here. I mean, this dim block, that's supposed to be the projective part, so that should be the first index, and the projective part should be contiguous, so it definitely should be as the inner dimension. In RowGather, the way we implemented, we are essentially iterating over the shared tensor in a non-contiguous fashion, which is not really the end of the world, but it could be. It could cause problems potentially. We could run into bank conflicts because of that. So it's best not to do it. Instead, what we'll do, yeah, we'll do a dim block right now, and then we're going to reorder, and it's going to be fun quote oh yeah, like this. And then now that it's like this, we can apply the innermost dimension using the index block. And we have the dim inner, which is 1. Oh yeah, we're reshaping this, so we don't need to index like this into the original tensor. Just oh damn, this is super wrong. Okay, in all shared, this is just the index block. We index with the first, now with the second, and why is this error? Oh fuck. Because it's not a vector, it's a dim, we cannot really assert that it's 1. Okay, loop product, I think, something like that. Loop prod. Calculates the integer product of the argument, yeah, like that. We just multiply all the elements of the dimension and check whether it's 1. That's what we need. We have the dim block for the linear part. This one we are applying outside the dimension. Free vars applies F. As for the dim, yeah, because this thing is just 1, we can use this as the dim index inner. Oh, no problem. No. I always keep wondering whether there is a way to, instead of trying to use this rigid merge, maybe you should be just using loop projector reverse everywhere. Like, I mean, oh wait, dim index. I mean, yeah, we should be able to use. We should probably be able to use the. Project reverse. Okay, let me just take a look at what that type of rigid merge is. I kind of forgot, you know, the entire chain of reasoning. Instead, so the rigid merge turns a dim. All right, and then projective reverse returns something else, and that something else is probably an integer. Yes, it returns an integer, so that's why we cannot. I mean, that's why it's not exactly the same thing. But you know, the split function, I mean, it's kind of weird that it's returning a dim. Like, doesn't the loop rigid split take in an integer? Rigid split. It takes in this and dim. It splits the dim into two, right? The rigid reverse just gets back the original dim. Okay, so dim block, dim inner, dim block, dim inner. Wait, does this really make sense? Like, we have the rigid merge. Oh yeah, the first index, yeah, that definitely should be multiplied by any of the other dimensions, because it's supposed to be the projective dimension. That's supposed to be less than the integer length of the index. Oh yeah, this does make sense. Okay, I see. Wait, so why is it like this? Shouldn't it be dim block and then dim block quote? Yeah, I mean, I just kind of did some evolutionary programming, as it's called, which is kind of trying things out at random until it fits, because I didn't want to bother thinking about the indices too much. I mean, it should be dim block and dim block quote, and then the index block. But of course, if we try doing that, we won't get a correct solution. And there's no chance, yeah, it's I and... it's I and dim. Wait. Where's the rigid split? It's dim and index. Yeah, it's dim and index. I mean, I don't know what to think about this. Like over here, we're kind of doing the wrong thing to get the correct result, if that makes sense. I guess we're kind of doing things because we're reordering the dimensions like here and so on. It probably ends up being due to something like that. Okay, but never mind that. Yeah, we kind of need to reorder the stuff here because we're kind of reordering the stuff here, which changes the strides. So that used to be the reason. Something like that used to be the reason, if I remember vaguely, but correctly. My memory is vague but correct. In this case, I think. Okay, so we have the thread ID. We have the index inner. And we're applying the index. I mean, yeah, I mean, this is complete. I'm not sure why I'm even thinking about this anymore. We can move to testing this out, I think. Let's give it a try. And this is the projective loop, and if we got this right, we should get the same results with the linear loop. Okay, first of all, let's actually let's just save this. Okay, that's one. Now let's try compiling this, and then we'll run this, and we're also going to save this. Now can we split the window? Okay, now let's look at these side by side. Okay, so this is 0, 0, 0, 0, 1, 1, 1, 1, 1, and this is 0, 0, 0, 0, 4, 4, 4, 4, 4. So one of these is wrong, and this new one is the one that's wrong. So the thread ID that we're calculating is wrong, I think. Okay, I guess we don't really need the split panels. We can just go between them and immediately see. It's actually even easier to do it on like to see the changes like this. What did I do? So I guess it should be like this, I guess. I'm going between these two tabs and I don't see any difference. Yeah, it basically works. I mean, I don't know why the dimension was being calculated incorrectly. I mean, it's correct in the row gather for some reason, but not here. It's weird. Okay, what if we made this like 8, for example? Yeah, now it processes it 8 times. And you can see what we want to do with this. We can use this to implement the loop in row gather. And this time around, we actually don't even need any inputs or output arrays in it directly. Instead, we can just implement that here. So let's see. I think I might just do a row gather completely here as an experiment. Let me close this. Done with the distributive linear. Or rather, yeah, the transposing loop. I forgot. It's supposed to be transposing linear loop. Let's do a few comments for both of these. Uses a shared tensor to transpose on the free variables in shared memory before running the function. Uses a projective loop for the loop itself. And the projective loop uses modulo operators, while the linear loop is simply goes from, it's a linear loop from 0 to some value. That's why it's restrictive. Inner dimension must be divisible by the number of threads. Yes, perfect. Yeah, I think maybe it's simply right here because, I mean, okay, never mind. Forget what I was going to say. I won't talk about this anymore. It's figuring out the tensor dimensions and how to index them is not a simple thing to reason out. When you're doing modular arithmetic and other kinds of arithmetic, it's very easy to make a mistake. It's not just fitting one type to another. So, okay. So we have the projective and the linear loop. What we should do now is re-implement the row gather in terms of that. So let's see, how are we going to do that? Let me pause here so I can add this video to the timeline. I am somewhat fatigued by
this. I don't know. It's kind of, for fuck's sake, it's kind of going. It's very hard going trying to move this forward. Like, I'm not really firing on all cylinders for some reason. I'm kind of very unsure about each step as I work on this. It's definitely taking time. Okay, so this row gather thing, yeah, we're going to re-implement it in terms of these functions. And this is going to be what? Okay, where is it? Transposing. Oop. I'm going to name it like this. I don't think it's going to be used that often. Replaces the free variables in the first argument. Those. They have to be all of them equal in number and type. I mean, I don't mean to say that all of them have to have the same type. Both of them have to be equal. Both of them have to have the same number of free variables, and the pairs of them I guess this is good enough. In case you're wondering, the reason why we are doing this linear loop is back then when I was doing the matrix multiplication kernel, I found that the CUDA compiler for some reason is not very good at dealing with projective loops. Maybe it's because of the modules or something like that, but I guess it cannot really determine the termination conditions for them properly. I don't know. Anyway, we got better performance by using linear loops, so whenever we can, we use them instead of the projective loops. That's why I wanted to do a linear version as well here, just because of that. Okay, now let's open CUDA core. Core CUDA. Open core base. Open transposing loop. Open core ext. Okay, now we're done with this. So let's think about this. We no longer need the shared arrays. We no longer need to set the input and the output pointers into the shared arrays. No, wait. How are we going to get to the variables outside the outside the projective and then linear loops. We cannot do the. We cannot just set a variable outside the loop and then. We cannot make a variable outside the loop and then set it inside it in order to get the stuff out, because it's going to be setting everything, setting all the free variables. Passing on the free variables through shared memory. It's one thing for something like a map tensor, but it's completely another thing for the reduction one. Oh damn. Okay, let's do it like this for now. I'm going to pause here so I can think about this more. Okay, I think we already have the answer. Let's go back to the projective loop, and instead of it returning unit, it's going to return arbitrary type. Okay, let's call it t. We're going to create shared out tensor int t, and if this t is a void type, then no problem. And we're going to do tensor set what is it, really thread ID? I guess it is thread ID. So I guess it has to be done like this, and then shared out. Oh yeah, this is going to be pretty good, and it's not. Yeah, it's not enough. We have to, at the end of this, at the end of all of this, yeah, I guess we just have to index into it, and that'll be. Let's do this. Tensor index, and this is going to be, I guess, thread index. Thread index and shared in. Oh wait, shared out. It should be shared out. And yeah, it's. Wait, what? Oh, god damn it. Oh yeah, like this. So it's, yeah, I think they should be fine. I'm just wondering, you know, about that potential compiler optimization that we are missing due to doing it like this. It's fine. It's fine. So now the projective loop is getting stuff out. We're also going to do the same thing here. T. Thread ID. Yeah, now this needs to be tensor set. We need to put parentheses around it. Good that the type checker warned me. Oh wait, what the hell? Barrier city async. This is supposed to be a unit type. Oh damn. Okay, where is it? And we need to index into it. Thread index shared out. Yeah, we just finish waiting until it finishes writing. But wait, is this really right? Will every thread necessarily have the same output in the linear loop, right? It might not be the case. Yeah, that's the Okay, great. Now I think let's go back to the test again. Test well. We're going to test this out. We have the linear loop, and here it is just returning unit. X. But what if we, for example, returned something else, like okay, did, and then console write ln. Oh wait, let's make it x. Alright. We'll make this x. Now let's see what we see coming out. Yeah, what we see coming out is exactly what we want. 0, 1, 2, 3, 4, the original thread ID. Okay, so let's also just try that same thing out, except for a projective loop. Oh, same thing. Okay, now we can get the return values out of these two transposing loops. Let me pause. And just one last thing, we should still make sure that returning the unit type works. Oh, yep. Void array set, and yeah, this is the return type. Void array index. Yeah, perfect. Implemented in the return transposing loop. Now let's finally get back to this. Now that we have the ability to return values from transposing loops, we can actually implement the reduction part of this. Okay, now we are set. We don't need this anymore. Oh, here it is factoring the from dim block inner, dim block, dim inner. This is basically transfer block. Transfer main block, dim inner. Index block, index inner. Now we're doing this projective loop. Okay, a bunch of this stuff I guess we'll have to set aside somewhere. I mean, we might as well, whatever, we'll put it here, something like this. And what we need to do is make sure that from to map and to reduce are have their indices applied and their pointers applied, because they'll be shared through global memory. So let's see. Yeah, here we are turning these into tensor fucking pointers and turning them out. Oh god, so this is... It's amazing that I decided to do it. But you know, it's not that trivial to think of this solution. When I realized that I could not share the reward very easily, it kind of acted like a blow to me, and it motivated me to think harder about the problem. If I hadn't done this version first, I never would have arrived at the better solution. So sometimes programming simply works like this. I cannot get everything right the first time around. Even this solution only really occurred to me because I had the experience of doing the UpMem backend. So that kind of eased me into the idea of taking a function and changing its slots. In this case, we are just changing the free variables. So this is how it's done. Wait, what the hell? Yeah. Okay, so we have the from. Let's think, what's the dimension of this? It's already applied. To reduce, this is an array. Oh, this is an array. Okay, since we can just since we don't need an explicit output here, we can just get rid of this completely, this case C. We can just say this return C, and if it's a unit, it will automatically be ignored. And that's the beauty of this these new loops and the changes that we did recently. Okay, to map, then the option, and regarding what I was saying, we only need to apply the pointers from the front tensor. You know, from equals from apply ptr, you know, to map equals for fuck's sake, let's see, how is this being dependent option map, yeah, like this, dependent option m map to map apply ptr. Oh, no problem. Oh, let's do it like this. we have to make sure that we aren't passing any more type variables. I mean, not type variables, but free variables at runtime than there is necessary. We don't want to pass in strides by accident, separate from the pointers. So here we just apply the strides. Here we just apply the offsets to the array pointers. And this is great. Now we can do a transposing loop, linear, and we can pass in the dimensions. And okay, what can we do here exactly? So I guess this is threads per block and demeanor. Yeah, it's basically this thing here. Of course, it's not the outermost demeanor that we get from here, but this inner one. We can kind of multiply the dim block times dim block rather than do this, but it's the same thing in the end. Okay, so this is fun, and this is okay, this is the thread ID, and this is what, the inner ID, dim inner, I mean index inner. And yeah, this is the index block basically, and okay, we'll be passing it in as the thread ID. We have this loop linear. Now how let me just open the test. Thread ID, thread ID and the inner index. And if you look at loop projective, we have to get the from and yeah, we actually don't need to get the from because we already have it. We can just grab it from lexical scope, and the tensor will have its pointer exchanged to the right one. Yeah, actually there is one issue, and that issue is that we also need to factorize it. Right, we need to oh yeah, we need to factorize it like this. Yeah, this is where we are actually factorizing it into dim inner, and so do we do it like this, or yeah, okay, we are going to reshape and then reorder it. Okay, let's do it like this. Okay, from reshape, reorder, yeah, index inner, where is this happening? Tensor. It needs to be a constant, right? const. And this is the index inner, so what's the problem? Oh, wait, why is it expecting index inner? All right. Wait, so then I mean, we already have the inner. God damn it, I shouldn't have erased the old row gather. Let's just get it from here. Yeah, this is basically a loop linear or a dim block, and now we are doing something else, so I'm getting confused. Okay, so this is the thread ID, and this is the index inner. So that's all right, right. Okay, I can get it now. But in that case, what's even the point of doing this projection here, like index block? Like this index block, isn't that the thread ID? Yeah, we don't need the threads per block. We get that automatically. So we have the thread ID, and that's something that we'll be using to... I mean, to do what exactly? Wait, why did we even need the index block? I'm so confused. Here we are shipping the from array. So we needed that to index into the shared array. Okay, that makes sense. And then we were doing this kind of thing, this ugly nasty thing. We're kind of reshaping the arrays. Yeah, now it's so much better. We don't need the index block, and we're going to get the index inner from the loop itself. Okay, and these two. Yeah, we have to load them into local memory now. Yeah, okay, I get it. I guess when you're considering code quality, you can think of something being as better, something as being bad, or something being good, but it's kind of really relative to... It's always relative to something else. it's never really good or nothing is ever good or bad in isolation. And the version that we're doing now is definitely better than what we had before. There's no doubt about that. Okay, so let's do this. Oh great, we're loading these tiles. Map the local tensor using local operations. Yeah, we no longer need this I. This is just going to be the thread ID. And we are doing these reductions. Okay, let's just do this. Yeah, it is possible to do a lot of things using GPU programming. This is pretty interesting parallel programming in my opinion. Okay, thread ID, threads per mini block. Wait, do we have that? Yeah, we do. Threads per mini block is the inner. Okay, we have the local map, local reduce. Why is that the type? I have no idea. So now, at least for the local map, we need to set the output. Here we have the here we are in fact just going to get the C out, and we have the dependent option. Okay, I get that, no problem. Okay, first, I guess we'll first take care of the local reduce case. No. The local reduce will just return at the end. So we have to take care of the map first. So let's see. To map. Dependent option m ether 2. What the hell is this? I guess the to map we need to we need to do this same thing as here. Apply index inner. Dependent option m. Okay, reduce. Oh yeah, we just have this then. Memory sync to from local. Where's this I coming from? Here it is coming from. Okay, I see. The inner. Oh yeah, very nice, very nice, very nice, very nice. Yeah, do we need yeah, we have this transposing loop, and it will put a barrier sink at the end, so it's fine. Oh yeah, this is very nice. That's the only way to describe it. Yeah, we definitely upgraded this. Right, and it's going over the dim inner, installing into local, and it's operating on that. Yeah, perfect. Simply perfect. Okay, so now we just have to do these row gather map reduce BC. We no longer need this. Row gather map. We just make the right side the unit type. There's no longer a need to mess with the arrays. On the left side is simply none now. On the right side is this. Wait. So it's like this. Row gather void. I mean, we can just do it like this now. And from none. None. Yeah, not bad. And we actually don't need a separate void implementation anymore. We can just use the reduce. It's no longer the case that Spiral cannot support the void arrays. We can support them just fine. So, okay, let's get rid of the void. I mean, we can just leave it in, whatever. It might be easier. I'm just wondering, we also did this same kind of refactoring for the row template, for the regular one. So what happened with that? Do we still need the void version for it? What about the reduce? I mean, tensor dim B, tensor dim C, yeah, and we cannot have tensor dim void usually, but now we can. Now that we've implemented the new type of array creation, we could have void arrays. You know, I'm a fucking idiot. Instead of hacking the tensor so it supports the void types, I could have just passed in tensor and then an empty record. For fuck's sake, I even remember myself saying like an hour ago that it's that an empty record wouldn't be a void type. It would just be pretty much nothing. It would map over the empty record type, and it would just still be an empty record. There'd be no array pointers that are void inside of it. Instead, I'm busting my head over here with unit types. Oh my god. I cannot believe I didn't put 2 and 2 together. I mean, let's test it out. Let's see what happens when we do this. Like, we're going to comment this out just for a bit, and we have the tensor 12. Yeah, this is now an empty entry function. When we do, let's say, t tensor int tensor create 16, what will happen? Open tensor m. What happens here? Yeah, pretty much nothing. When we do a void type, yeah, it has this annoying void array creates. Oh. In fact, this kind of pretty much invalidates the entire reason for passing those optional types into the. I mean, it doesn't into the row gather kernel. It doesn't invalidate it completely, because we might have runtime dimensions, except we don't, because we explicitly check that they are literals. But if we allowed the inner dimension to be a runtime literal, let's see, where are we doing this? Like maybe in the future we might decide that 2dim should be passable at runtime, and the from-dim should also be passable at runtime. We might want to, for example, just assert inside this assert inside the transposing loop that they are the same. We might want to do that, for example. Then in that case, this dependent option might be useful, but right now it's pretty much completely useless. We have the void types. We can just use an empty array. I mean, an empty record instead of a void. Okay, yeah, I mean, now you can see it. I don't get everything the first time around, and don't get everything right the first time around. And there was a much better option the entire time, I just didn't see it. don't need this anymore. I mean, we don't even if they're only, even if, for example, hypothetically the dimensions were only known at their runtime, what we could have done is simply passed we could have asserted that the runtime variables, that the runtime variable containing the dimension of the from tensor is the same as the runtime variable containing the dimension of the to tensor. The spiral partial evaluator does track this kind of aliasing even in join points. So if that's the case, it would just be the same runtime variable. Okay, so not bad. Okay, let's just make this 2. Okay, I guess we can make this 2 map. Not bad. I'll just put this on the same line. Not bad. I mean, we could even zip it. We could even zip this. Zip to from. I mean, we can just do it like this, like to map zip from. Yeah, why are we even fucking doing this? We can just do let's make this IO. Wow, it's like getting a superpower. We don't have to pass in separate tensors. We can have the input and the output be in the same one. IO, input output tensor. Apply all the pointers. Now we don't need to zip it. We can just pass the IO into this, and then we just do unzip. Bam. And now over here, we don't need the. What the hell is this? I mean, we don't need this anymore. And okay, this is what IODIM 2. And let's make this like 2. So what exactly is the problem here? Tensor B, C, this is B. Okay, this is B. This is local map, right. And do we have some? Yeah, we have also a local. I guess we have a local in. I mean, this is in the local in, and this is the local out. Okay, good. Now let me show you how we'll implement the gather map reduce. So instead of doing this, we can just zip from and to. Yeah, we don't even need to separate them out anymore. This is map reduce, and this is just map. Okay, we'll zip it again. Zip. Over here we're just doing type-driven development. It's no big deal. And now we can do the reduce. And this thing over here, we'll just create a tensor and set its value to an empty record. I mean, I simply wasn't aware of the value of the empty record until now. Okay, this is just going to be like tensor create xnim. And this is going to be zip tensor create from dim, and of course it doesn't know what the type of this is, so we're going to give it perfect. And because of the magic of type impermanence, it knows that this is also an empty record. And this won't create any pointers. It will in fact have potentially have if the dimensional from is a runtime variable, it will then this will also be a runtime variable in this tensor. But we are kind of checking that it's known at compile time, so it's not a problem. I mean, even if that wasn't the restriction, maybe the strides would end up being different, but yeah, it doesn't matter, whatever. Like even if this was a runtime variable, like this from dim, the stride would still be 1, since this is one-dimensional. The stride of this tensor being created would just be 1, and the offset will be 0. It's no problem at all. I mean, actually, no, I'm getting this wrong. It's not the tensor itself that has the strides or the offsets. The individual tensor bodies have the strides and the offset. And because we are using the empty record as the type, it won't have any tensor bodies. It won't have the array, it won't have the strides, it won't have the offsets to pass into the projective loop through the shared array. So yeah, this is very efficient to do, and that's important. And we have this row gather void. Yeah, we'll be returning the same thing as here. I mean, but it doesn't really matter, since since this is not a problematic situation, like we could probably get rid of the row gather operations entirely. And yeah, now we have this row thing, and it has this to map. We could also put that in the same thing. Okay, I guess we'll refactor this, even though it's amazing. Somebody should come in here and teach me how to use my own language. I don't know shit. I'm officially bad at programming. And yeah, we don't need the from and to, we can just zip them into one. Even though this kind of leads to, it will lead to worse messages, but whatever. To reduce. Yeah, you know what? I mean, this kind of it's true that we could refactor it like this, but this kind of refactoring could introduce errors, and it's kind of making the error messages worse. So yeah, let's not do it. Let's leave it as it is, even though it's kind of not as good, not as elegant as the row gather solution. It's my fault. I've been teaching you how to do the wrong thing here. Oh. But yeah, there's nothing wrong with this kernel if we consider its correctness. Like, are we... I mean, maybe I should do some printing to make sure the strides are right, but it should be fine. Yeah, the inner strides come to the fore instead. Wait, the front. Do I mean the front as the outer dimension or the front as the inner dimension? What the fuck is the front here? Yeah, basically this is splitting and then swapping. So the inner dimensions should come out. That's what this means. I mean, I guess, yeah, it's fine. I guess it's, yeah. I don't feel like messing around with it, trying to redesign it once again. You know, it's fine to do it for row gather, but over here, meh. We had to redo row gather completely. Okay, note. Let me just leave a note. Not enter. Eight 2024. Before actually zipping this, I am going to do a little assert in map and map reduce, just to make the error messages better. From just zip will already assert. Okay, I think we should test this out next. It's really amazing when you think about it. We spent all this effort just working on a single loop. So yeah, so don't underestimate loops. Loops are simply so integral to the life of a programmer. Anything you learn about how to do loops will pay dividends in the future. Okay, I think I need a break right now. Let's put this to the timeline. Okay, let's finally move on to testing. I simply had to take a break because I was thinking so hard and it fried my brain. Right now, this simply came out so damn well. It's amazing. Oh yeah, I love this. I love it a lot. Not really necessary. This one is... No, I'm not going to leave a note that this is unnecessary. Who cares? Yeah, it might as well stay here. I don't want to test row map reduce and the regular row template functions again, so we are also going to leave it in as well. No problems here. We're going to need to test the row gather map, all of these tests again. I mean, okay, let's see what's going on here. Input action, row create, sample reuse. Okay. Well, let's go through this from top to bottom. Okay, well, what's the input identity? That's the input. Well, whatever. Let's print it out. Build, Control B. Let's open the sidebar. Primitive spy. We don't need this anymore. Build, run. And assuming all of these tests, they aren't passing. What's going on? Reference variable v451 requires an initializer. Array of reference is not allowed. No. What's going on here? So this is the Philox thing. Why is this giving us an error? Yeah, this is a reference. Oh, it's trying to share the RNG. Oh. Yeah, it's trying to share this RNG reference. Okay, where's that happening? It's happening in local mass, softmax, and discrete sampling. Oh down. What exactly was my plan for dealing with this? I have no idea. I mean, I didn't even think about the RNG. I just thought that there might be variables which we want to keep on a single thread. But I can't really thought about this specific case. Like, I mean, this isn't that hard to fix, at least for this test. What we could do is like, okay, let's just move this in here.
this should resolve the issue, but do you want to do that, or do you want to keep this RNG outside? Like, this RNG, this is one thing that I had actually considered keeping on the thread. It's definitely not necessary. Okay, I don't know. I mean, we could extend the row gather operation to allow passing of arbitrary values into the kernel, which won't necessarily be swapped. I mean, transposed. Do we want to do that, or do we want to do it like this? Okay, I'm going to have to think about that, but I'm going to leave that thinking for later. For now, this is just testing for correctness, so it doesn't really matter if this phylox state is being initialized right here. Who cares? Fuck it. Build file, primitive. Okay, I need to put some energy into this. You know, one thing we could... You know, one thing we could do is actually generate the probability like outside this kernel, then pass it into the discrete sampling kernel, like sample an uniform probability like somewhere here, then pass it in, and not have it in this discrete sampling at all. And that way we could avoid having to actually do the reduction step, you know, to generate it. We could avoid having every single fucking thread generate a uniform number and then have to do a reduction to share it across the threads. I mean, even so, I mean, that would make sense for original discrete sampling that's being run in row gather, because the row gather would automatically share the probability across all the threads where it's needed. But for something like a regular row map or row reduce, and that's a different thing entirely. Great, now I'm thinking about this instead of running the test. I mean, could we somehow generate the probability outside in... No, we can't do it in regular row map. It simply has to be like this for row map. And indeed, for a row map, okay, forget it. I won't think about this anymore. Let's just check out the results. Build file, run. 2121100.
Okay, this is fine. Indices map. (31 0, 31 1, 31 2, 31 3, 4. Indices reduce. Fine. Okay, I guess we'll print out the input. I mean, this isn't much to look at. Output op map. What's that? Is that maybe 10H? I forgot. It's local mask regret matching. Oh yeah, this is fine. Output identity map. Okay, these two are kind of hard. Okay, here's what we're going to do for this particular one. We're going to zip it with the input. I should have done that a long time ago, instead of trying to paste them in side by side. Oh yeah, it's fine. Let's also just make sure that it's doing the right thing with larger sizes, like like 256 maybe. On the device side, assert triggered. Oh, I triggered. Tensor range check. 0 6. No, what the hell is this? I mean, I can't remember something like this happening before, but I forgot. Yeah, did we? Yeah, we had issues with the softmax, I think, with larger values, but I have no idea why we're getting problems now. Tensor range check. I mean, at least we know that something is wrong, but who knows what. So we have no choice. Let's comment this out. I'll comment this out. This is input indices map. Oh, let's see what happens when we run just this. Yes, it's still triggering some kind of assert. Okay, so this should be of size 256. It will factorize it. Then the inner dimension will be 4. Okay, so I mean, then the inner dimension will be 64. I mean, once it factorizes it by 4, once it factorizes 256 by 4. So okay, no way around it. We're going to have to debug. We're going to figure out. We're going to have to. Yeah, this is actually a device side assert. So it's indexing into something incorrectly. If there was an error here, we'd get an error at runtime. So, oh, sorry, I started sneezing. While I was having a fit, let me go over what I think the problem is. Like, ME is like 16 here, but it should be covering the entire thread. Like, this should be threads per block. Why the hell do I have this here? Threads per block? Yeah, now let's make it 8. In row gather, the M always needs to equal threads per block. Currently that's 32, no way around it. And wait, I'm a bit confused. How did I even run it last time? If okay, sorry about that. I'm very confused right now. I mean, yeah, I am commenting this and commented this in, so that's, oh yeah, I'm so, yeah, that commented out part was what was tripping me up. Okay, let's try it again. Oh yeah, this seems right. Let's go over all of it. And the indexing that was causing trouble is this here. And it was right. It's great that we had the asserts on. Otherwise, we'd be running erroneous code. Okay, so this run. Oh yeah, we already tested the indices map. We'll test out indices reduced, though I'm sure that should be right as well. No problem. Oh no, there's no point in printing out the input. I mean, this is just a ton of zeros because it's masking out all but the first 3. Yeah, it looks correct. This is 1, 6, 44, 49. This is 1 over here. Oh, 8.5, 17.9, 73. Yeah, I mean, yeah, this is very likely to be fine. Let's just check out the output identity map and then we're done. Uh, 16 minutes. Ah, yeah, this is fine. No way, this is wrong. Okay, good enough. And I think we'll probably end this video here and go back to working on tabular counterfactual regret. It's been very educational even for me to do all of this. I think this is pretty interesting GPU programming, I think. Like, you wouldn't be able to do something like this in C++. Yeah, you know, imagine having to deal with all these fucking lambdas in C++. Oh my god, that would be a nightmare. You simply wouldn't be able to write code like this in any other language than Spiral. And if you want to write a machine learning library and a poker agent, this is the sane approach to take, I think. But whether it's worth doing all of this to begin with, that's an entirely different matter. And it's going to be obvious only in hindsight. So maybe in the future people will be watching this and wondering, wow, this guy is very good. Or maybe they'll be thinking that this guy is some kind of lunatic. I don't know. I don't have the power to, I can only have the power to keep going forward. Real life is just too difficult. So let's make a commit. We are done with testing. I think, well, we don't need to test out the regular raw template because we haven't done any changes. That really makes it a lot easier. You know, it's kind of tempting to just, once we figured out this more elegant way of doing it, to use the new pattern, but then I have to make the changes and then I probably break something and get weird bugs down the road. It is possible that the testing that we've done here isn't sufficient because we're not doing that much testing to begin with. It's very hard to test machine learning operations. Who knows what kinds of bugs we'll run into in the future. Even for testing tabular CFR, we only have our only option is to just print things out as we go along and think really hard about it. But that in fact has been working for us, so we might as well keep at it. Done with testing. We're going back to working on tabular CFR. Personally, I think what we're doing in the series is amazing, and I hope that at some point other people will be able to recognize this. I feel that I deserve better treatment than the one given to me by the job market. I want the high-paying jobs. I want people to come to me in recognition of my skills. I shouldn't have to apply to like 100 different places, getting rejections everywhere. It's ridiculous. I'm using the wrong shortcut. Oh yeah, so we're going to end this here and we're going to continue from where we left off. Now that we have now that we've changed the row gather map reduce, this reward is in fact going to be the correct reward for all the threads. And for the stuff here, we should be applying the pointer everywhere. But okay, I'll leave making the changes for the next video. Let's stop this here. See you in the next one. Bye bye.